let's just do this today. And I'm not going to worry too much about that. So multi-data, detecting concurrent writes. Dynamo-style databases allow several clients to concurrently write to the same key, which means that conflicts will occur even if strict quorums are used. The situation is similar to multi-leader replication. See handling write conflicts. Yeah. Although in a Dynamo-style database, conflicts can also arise during read repair or hinted handoff. The problem is that events I just realized something that's super annoying. Just no more juice. That's right. The problem is that events may arrive in a different order at different nodes due to variable network delays and partial failures. For example, figure 512 shows two clients, A and B, simultaneously writing to a key in a 3-node data store. Node 1 receives the write from A but never receives the write from B due to a transient outage. Node 2 first receives the write from A, then the write from B. Node 3 first receives the write from B and then the write from A. Let's go over that one more time. Node 1 receives the write from A. Okay, so there's 2 writers, 3 nodes, but never receives the write from B due to a transient outage. Okay. Node 2 first receives the write from A, then the write from B. Okay. Node 3 first receives the write from B, then write from A. Okay. If each node simply overwrote the value for a key whenever it received a write request from a client, the nodes would become permanently inconsistent as shown by the final get request. A get to A becomes what A because it gets A. We never got B. Okay, we're going over this again. I don't really understand. What is it supposed to be? They're concurrent rights. Mm. I really want to take notes on this. I have a flashcard for these. Um, Just finish this. How do we decide whether two operations are concurrent or not? To develop an intuition, let's look at some examples. In figure 5.9, the two writes are not concurrent. A's insert happens before B's increment because the value incremented by B is the value inserted by A. In other words, B's operation builds upon A's operation, so B's operation must have happened later. We also say that B is causally dependent on A. On the other hand, the two A's are concurrent. When each client starts the operation, it does not know that the other client is also performing an operation on the same key, thus there is no causal dependency. An operation A happens before another operation B if B knows about A, or depends on A, or builds upon A in some way. What the fuck? Is that English? Whether one operation happens before another operation is the key to defining what concurrency means. In fact, we can simply say that two operations are concurrent if neither happens before the other, neither knows about the other. Thus, whenever you have two operations, A and B, there are three possibilities. Either A happens before B, B happens before A, or A and B are concurrent. What we need is an algorithm to tell us whether two operations are concurrent or not. If one operation happens before another, the later operation should overwrite the earlier operation, but if the operations are concurrent, we have a conflict that needs to be resolved. Yeah. It may seem that two operations should be called concurrent if they occur at the same time, but in fact, it is not important whether they literally overlap in time, because problems with clock and distributed systems, it's actually quite difficult to tell when two things happened at exactly the same time, an issue we will discuss more. For defining concurrency, exact time doesn't matter. We simply call two operations concurrent, so this is actually pretty interesting, if they are both unaware of each other, regardless of the physical time at which they occur. So offline mode. If I update a value on my phone and then a value is updated on my desktop, and then they sync, right? That's technically concurrent even if they happen hours apart. Interesting. People sometimes make a connection between this principle and the special theory of relativity in physics, which introduced the idea that information cannot travel faster than the speed of light. Consequently, two events that occur some distance apart cannot possibly affect each other if the time between the events is shorter than the time it takes light to travel the distance between them. Yeah, that's what I was confusing. In computer systems, two operations might be concurrent even though the speed of light would in principle have allowed one operation to affect the other. For example, if the network was slow or interrupted at the time, two operations can occur sometime apart and still be concurrent because the network problems prevented one operation from being able to know about the other. This is crazy, bro. What? I literally have no idea what this is talking about. I'm like so close to finishing this replication thing, and it's like just absolute hell to get through this. What? The server maintains a version number for every key, increments the version number every time that key is written, and stores the new version number along with the value written. When a client reads a key, the server returns all values that have not been overwritten, as well as the latest version number. A client must read a key before writing. I don't know what I just read. When a client reads a key, the server returns all values that have not been overwritten. The client must read a key before writing. When a client writes a key, it must include the version number from the prior read, and it must merge together all values that it received in the prior read. The response from a write request can be like a read. I literally can't follow this. I don't know what it's talking about. Come on. When a client writes a key, it must include the version number from the prior read, and it must merge together all values. The response from a write request can be like a read, returning all current values, which allows us to change several writes, like the shopping cart example. When the server receives a write with a particular version number, it can overwrite all values with that version number or below, since it knows that they have been merged into a new value, but it must keep all values with a higher version number because those values are concurrent. So basically, what we're saying here, so in client 1, we write milk. This happens at the same time eggs, right? So when we set the key, we pass in version 1. When we look at the database, there's a version higher, which includes eggs, which means we can't overwrite eggs. We have to maintain this, but we can merge the data, and that's what's happening here. We keep merging the data. Okay. I think I finally have some semblance of what's going on. I think that was that. Oh. Oh my god, dude, there's so many problems to deal with. This is all just for adding. What if you want to remove stuff? Oh my gosh. It never ends, bro. God. Um, 6 minutes to finish this last thing. All right. This. Bro, I'm not gonna lie. If I ran into this problem, it would just be impossible. I'd be like, yeah, we can't do this. God. Why do they do this, bro? All this stuff needs to go away. Holy cow. In this chapter, what the... I mean, this is tough stuff. In this chapter, we looked at the issue of replication. Replication can serve several purposes: high availability, disconnected operation, keeping the system running, allowing to continue working with network interruptions, latency, and scalability. Despite being a simple goal, keeping a copy of the same data on several machines, replication, turns out to be a remarkably tricky problem. It requires careful thinking about concurrency and about all the things that can go wrong and dealing with the consequences of those faults. At a minimum, we need to deal with unavailable nodes and network interruptions, and that's not even considering the more insidious kinds of faults such as silent data corruption due to software bugs. We discussed three main approaches to replication: single leader replication. Clients send all writes to a single node, the leader, which sends a stream of data. Yeah, multi-clients send each write to several leaders, follower nodes, and then leader lists where everything can write. Each approach has advantages and disadvantages. Single leader replication is popular because it's fairly easy to understand. There's no conflict resolution to worry about. Multi-leader and leader list replication can be more robust in the presence of faulty nodes. Replication can be synchronous or asynchronous, which has a profound effect on the system behavior when there is a fault. Although asynchronous replication can be fast when the system is running smoothly, it's important to figure out what happens when replication lag increases and servers fail. If a leader fails and you promote an asynchronously updated follower to the new leader, recently committed data may be lost. We looked at some strange effects that can be caused by replication lag, and we discussed a few consistency models which are helpful for deciding on how applications should behave under replication lag. You have to write consistency. Users should always see data that they submitted themselves. That's right, monotonic reads. After users have seen the data at one point in time, they shouldn't later see the data from consistent prefix reads should always be in the same order. Yeah. Finally, we discussed the concurrency issues that are inherent to multi-leader and leaderless replication approaches. Because they allow multiple writes to happen concurrently, conflicts may occur. We examined an algorithm that a database might use to determine whether one operation happened before another and whether they happen concurrently. We also touched on methods for resolving conflicts by merging together concurrent updates. In the next chapter, we will continue looking at data that is distributed across multiple machines, the counterpart of replication, splitting a large data set into partitions. Fuck, dude, I don't even want to think about partitions. Well, okay, so we made it through a chapter. That took forever, dude. Wow. I don't even want to think how long this chapter is. I think what I'll do here is I'll pause for a second. Let's try and beef up and get back on track with the flashcards. There's just so much information here that I don't really want to forget. So anyway, we'll tackle it next time.